All right, so chapter 15, talking about temperature, heat, and expansion. And just looking through the intro here, tough call on who to give contribution to for heat. A lot of people contributed. They chose Rumford here. I'd still have to go with Joule myself since Joule has the unit for energy. Heat is energy, and so heat does have units of joules. A lot of people contributed to heat though, but there's a quick introduction about that person. But getting to 5.1, temperature. And temperature is not energy. So heat being energy in joules, and then temperature being in either Fahrenheit, Celsius, or Kelvin. And they're giving a silly little picture here that if you put your fingers in hot and cold water, that when you pull them out, one's going to feel hot, one's going to feel cold. And they're just trying to illustrate the simple idea here that there's heat transfer. That in the case of the cold water, heat is actually leaving your body to warm the cold water a little bit, which is going to leave your hand feeling cold because energy is leaving your hand. And in the case of the hot water will give your hand energy, and that's going to make your hand feel warmer. And so I guess the hot probably makes sense for people. You know, as you get more energy, your hand feels warmer. But with cold, there's, back in the old day, they used to think there was some flowing type of liquid, but cold is actually the heat leaving your hand. So it's not like cold comes into your hand. It's that the heat leaves your hand, and then your hand feels colder because of it. It has less heat then. And they go into the temperature scales here. So, the most common ones we experience, Fahrenheit and Celsius. Fahrenheit was a person, and both of these temperature scales are actually arbitrary, meaning they were just chosen. Fahrenheit was chosen to try to align with a person's body temperature. He tried to get that to be 100 degrees, but 98.6 is what it ends up being today. Celsius was calibrated using 0 being the freezing point of water, freezing point, and 100 being the boiling point. So they were calibrated differently, Fahrenheit and Celsius. Celsius is more commonly used within countries, but the actual scale in physics is Kelvin. And if people are going to advocate for some temperature scale, I myself would go for Kelvin because that is what we use. And they make a statement about that coming up in a second here. But so they're, with these three pictures, they're describing different energies that can take place. And translational energy is when something just moves. Like when my pen moves, it has a translational energy. Energy is something we consider with motion like it's going somewhere. It's going to go from point A to point B. That motion we would call translational motion. And there's an energy associated with that, call that kinetic energy. Rotational motion is just when something rotates. So it takes energy to rotate. I mean, you can see my pen doesn't rotate if I don't give it some energy to rotate. And so we call that a rotational energy there that can happen. And also, they're talking about vibrational one to see. At the atomic level, atoms are connected by bonds. And as heat comes into the atoms, these atoms can jostle back and forth like they're connected to a spring. So, pretty common approximation actually for the atomic world to treat atoms as being connected by a spring. They kind of jostle back and forth, and we call that vibrational motion. And so we have these three energies that you're talking about, motion, rotation, and vibration. And they just want to point out on which one contributes to what we define as temperature, and that's the translational motion. So when things move around from point A to point B, that energy is what we associate with temperature. Things rotating and things oscillating, we don't consider as contributing to temperature. And that's the point they're trying to make there. Translational motion is the one that contributes to temperature. And they give an example of a microwave oven. Microwave oven knocks the molecules around, giving them translational motion as it knocks molecules around, and that's what causes heating to happen in your food. And that's what I have to say. I know there was something about Celsius in here. But something I do want to say back to the scale is that from 0 on Celsius, from 0 to 100, that's 100. It's a number. The difference is 100 for ice to boiling. Whereas with the Fahrenheit scale, ice freezes at 32, but it boils at 212. And so that's a 180 degree difference. So there's a 180 degree difference for Fahrenheit between freezing and boiling, while there's only a 100 degree difference for Celsius between freezing and boiling. And the point that's going to be made in some of the homework questions is which degree change is more of a change. And referring to Celsius, that this increment is Celsius is a larger increment of temperature than Fahrenheit is. Fahrenheit needs 180 to make a change from freezing to boiling, while Celsius only needs 100 to go from freezing to boiling. And so there is a question in the homework about which of these represents a larger scale. And they're talking about Celsius here. That's 1 degree change in Celsius. So 1 degree change in Celsius, that degree change is larger than 1 degree change in Fahrenheit. And so that's just something I wanted to point out real fast with the scales. You can see that with the numbers here that the change is less for Celsius. Heat. So heat is energy measured in joules. And with these 2 beakers of water, the beaker that has the larger water, so they're saying if we add the same amount of energy to both of these beakers, well, then that energy in the smaller beaker here, the smaller water, this is going to be a higher temperature because the energy only has to go in this little bit of water, where with the larger water beaker here, the energy gets distributed through all of this water, and so the temperature won't be raised as much. So the temperature depends on how much heat you're putting in here. And that's an example they're trying to give. If you give both of these jars the same amount of heat, then the one with less water in it will raise to a higher temperature because there's less mass here to absorb the heat. And so each water molecule absorbs more heat because there's less water there. I always like reading these captions because they're usually kind of silly. Heat is like love. It's not something you can be. It's only something you can give and receive. That's, I don't know. First thing that comes to mind actually is cats. We used to say a cat's in heat. So I don't know. Just kind of a goofy little saying, I guess. This one is good, though. This saying is good. Dark is the absence of light. That is actually in physics how we define black, say the color black. The color black is literally in physics the absence of color. Specifically, color that we see is from electromagnetic radiation. And all the colors are in that spectrum. And when there's no electromagnetic radiation, which is what we also call light, then all there is dark. And cold, this is what I was saying before, cold is the absence of energy. So that's also a really good statement too. So it's not like cold flows to you. You get cold because you're losing your energy. And they talk about the calorie here. I've mentioned the calorie before. This comes from the caloric theory, an outdated theory on heat. And the calorie still sticks around as a word, almost predominantly in food. I don't know that it's used anywhere else besides kind of nutrition stuff. And they're just telling you what these conversions are. There's the small C calorie. There's the large C calorie. But there's no homework questions on that or anything. And its importance there is, just for food. So specific heat. And so what they're getting to here, this person biting his pie, is that material has different, what we call specific heats. In other words, this piece of pie here, I'm guessing they're trying to show here, is that the crust on the outside, that's a different material than the apple pie that's inside. And so these different materials may require different amounts of energy to heat. And we call this quantity ultimately specific heat. That material has some specific heat to it. And an analogy I like to give is, let's say that to increase the apple pie part, let's say we want to increase that by 1 degree. Well, that may take a large bucket of energy to do. Whereas the crust, if we want to change the crust by 1 degree, then that may need just a little bucket of energy to do. And we call this the specific heat capacity. How much energy does it take to increase something by 1 degree? The smaller the heat capacity, the less energy it needs. So we would call this a small heat capacity. It doesn't have a lot of capacity for heat. Remember, heat is energy. So something that has a low specific heat, we say it requires a low amount of energy to change by 1 degree. And as something becomes a higher specific heat, that means it can handle more heat before it changes by 1 degree. So that's the example I'm sure they're trying to give with the pie here. I'm sure they're saying that the filling of the hot pie is hot while the crust has cooled off. And that's because they have different properties. And the crust requires less energy to change by a degree. And this is true for heating and cooling. So if you want to heat your pie up, well, the crust will heat faster because it requires less energy to change by 1 degree. So if you want to heat your pie, say it's cold, you want to heat it, well, the crust will heat more than the apple part will because it requires more energy to heat. Now, if we look at cooling, which is what this picture is actually a state of cooling, well, the crust will cool faster because it requires less energy. As it gets rid of its energy, only a tiny amount of energy will change the degree, where the apple pie part, it's going to have to get rid of a lot of energy before it changes by 1 degree. And that's the picture they're trying to represent here on why the apple pie part stays warmer longer than the crust, because they have different specific heats. They can both handle a different amount of energy to change by 1 degree. And this is all in Celsius, by the way. There is an equation here, which I just want to tell you is not in any of the homework, so you don't have to worry about that. This is specifically the energy for specific heat, where C, they have a little C in here. That's the specific heat capacity, and then mass being whatever your mass is, and delta T being your change in temperature. But that's the math equation there, but we actually don't use it anywhere in the homework. I guess I just threw it at you in case you wanted to see it and how we calculate that mathematically, but it's not used anywhere. And so water is unique for many reasons. One of them is it does have a very high specific heat capacity. So say just looking at my piece of pie here, if I have a body of water then, well, this body of water will require an even larger bucket. I'm running into my water there, but a body of water requires an even larger bucket of energy to change by 1 degree. So water has a very high specific heat capacity, and that's what we're going to talk to you and how that helps maintain temperatures. So, as the temperature changes on the land, well, the water won't change as much because it requires more heat to change by 1 degree. And it also helps with cooling too, stabilizing the temperatures. I read this before, and well, if you can make sense of it, more power to you, I guess. They're just making the comment here that climate is about the overall behavior of what's happening with our atmosphere, where weather is what happens on our day-to-day basis. So climate is what we call that happens over years of time, where weather is what happens day by day. And then they make the analogy that climate refers to the type of clothes in your closet, and weather refers to which you wear each day. So I guess weather is what happens each day. Climate is what happens over longer periods of time, though. So I'm not quite sure the reference to the closet. And that's just about water. And I do have to say that I don't remember where the part is, but I was looking at the homework questions, and there was a very specific part of the question. And I'll come back to that when I find the question here, but I'll show you where it is in the book here to find a very, very specific answer they're looking for. But looking at thermal expansion, so when you heat things, and talking about the atomic scale again, and it's not really a big problem to think of these molecules as being connected by a spring, so you can kind of get the idea that they vibrate back and forth. And the more heat you add to this, the greater distance they start oscillating from each other. They start getting farther apart. And ultimately, this causes things to expand when you heat them. And that's what you're talking about here with thermal expansion. There is also an equation for this, but there's actually no equations here for chapter 15, if you're just wondering here. So that's why I'm just drawing pictures. There are no equations here we'll be using for chapter 15. More just an overview of stuff. This is a good picture here. Why do bridges kind of have these joints? And this is to help with thermal expansion as things get warmer, that you have to leave room. So you have to leave room for things to grow a little bit. So we got some spaces here, room for things to turn a little bit as things grow slightly. And they have another picture here of these, I don't know what you'd call these, kind of zipper type of thing here. But this is also meant to be for thermal expansion. I suppose maybe it could be used for water drain off. That's what I used to think as a kid. It's like, oh, the water goes in there. But you can see, and it's hard to see with the cursor, my little hand cursor here, but you can see with this kind of zipper that there's these spaces at the end, and that's what allows the road to grow as it expands from heat and not damage the road. So that's why, a big reason why where you have a winter that's cold and a summer, which we don't have in Phoenix, but say in the Midwest, the roads tend to get cracked a lot in those areas because of thermal expansion, that during the summer the road heats up and that causes it to buckle. And, for instance, as something heats up and it's constrained, you can start getting this buckling effect that happens as things expand because it's trying to grow. It's trying to grow longer, but it's confined to this area, and so it starts to buckle, and that can cause the road to crack. And then during the winter, things will shrink, and that can also cause cracking of the roads. And we don't have that problem that much in Phoenix, though, since we don't have cold winters. And this was something cool here. I thought, I'll come back to this video. I'll come back to that video. They're actually showing a picture of thermal expansion here, which is pretty cool. And I was reading this section. Well, I read all these sections, but what was interesting here that I never thought about, but what they started doing is they started laying the tracks in the summer months. So what they decided to do is lay these tracks in the hottest time of the year so that it was at its maximum expansion. And then all the time of the year it would be colder. And so this would stretch out, and stretching steel, as long as it doesn't stretch too much, isn't a problem. And that's how they ended up solving this type of thermal expansion. So I don't know the exact history of this picture, but according to the blurb here, it looks like a train crashed, that there was a hot summer day and the rail line started to buckle, and the train couldn't stay on that. And so, interesting solution. Just build a track during the hottest time of the year, and then you'll never have thermal expansion. It'll always be contraction, and the steel, as long as, again, the contraction is not too much, the steel won't rip itself apart there. So I thought that was interesting. Didn't know that was a solution there. But going back to this video here, if you want to check it out, here's where they talking about this again. And I thought this was pretty cool that they mentioned this. But they're showing this picture of a candle, and you have iron and brass. And so they're talking about we as humans building this material that's got two layers. That they're talking about, the top one is brass, and the bottom one is iron. But they have different thermal expansions. The brass will actually expand more than the iron will with the same amount of heat. And so as this expands more, it causes it to curve. And that's what they're showing here in this first picture. The middle picture is where we should start. At room temperature, you can see they have it as a material in two halves there. And then they're adding the candle, and it bends. And if you freeze it, is what they're showing in the right-hand side with the ice block. If you freeze it, it'll bend the other way. And this is a clever way to make a switch. That if things heat, it'll switch down. If it cools, it switches up. It's I think a very clever way we've learned to make a switch, and something we use with thermostats and in refrigerators and stuff. How do these things know to switch on if they're too warm, like your refrigerator? Well, humans have come up with a lot of creative and clever stuff, and this is one of those things I think is pretty creative here. They're calling this the bimetallic strip. They talk about old thermostats here. So new thermostats aren't like this anymore, but old ones used a little blob of mercury, and you had this spring that as things would heat, the spring would grow longer. As things would cool, the spring would grow shorter. And this blob of mercury would cause the blob of mercury to lose. So these curly wires they're showing, these curly wires are meant to be the circuit. And when the mercury moves away, it disconnects the circuit, which then shuts the thermostat off. But as things warm up, then the mercury gets closer to the contacts, eventually makes contacts with the wire again, and mercury allows electricity to flow through it. And so that creates the contact, and it turns the thermostat on. And then now your thermostat is doing what it needs to do. So another clever little device humans have come up with. Got a lot of clever stuff. Here they're talking about putting a ping pong ball in boiling water. I have to say I've never tried this. If you dent a ping pong ball and put it in boiling water, well, the hope would be that the heat from the boiling water would cause the air inside to expand. So the hope is that with your dented ping pong ball, that as you heat the air inside the ping pong ball, that starts causing more and more pressure against the outside of the ball, hoping then it will just pop back open. And I could see that being true, but you also depends on how much that ping pong ball can handle not being melted and stuff. And dense. Once you dent something, there always tends to be some type of kink that you can never. Tends to leave a permanent damage to the material. Some kink in it that's usually pretty hard to get rid of. But another interesting little thing, I suppose, if you wanted to try that out. And they're talking about the expansion of water here. They go into a lot of detail about the expansion of water. And then there's no homework questions that focus on that at all. And so it's kind of a strange position from my perspective, because I like to have questions related to the material that's being talked about. And if there aren't questions, then I tend to say this is more a topic for your interest if you want to check out. And so that's what I'd say about the expansion of water. Water does have a lot of good properties or interesting properties. I was meaning in a sense for life. because our life as we know it, highly dependent upon water. But water has a lot of interesting properties to it. And one of the things they're just talking about here is that there's a graph, specifically this one right here that I'm trying to circle around, that they're showing the volume of water. That ice is less dense than water, and as you warm up water and break it from its solid stage, its volume actually becomes less, which is not something that traditionally happens with material. It's something that's unique with water, and they're trying to explain that here with this picture right here. That while water is in its liquid state, all the molecules are bouncing around. They're not connected to each other. But when things on the atomic level, when things want to bond, it depends on the properties of the atom itself. But there's different structures that the atomic level likes to build itself in. The most common one that maybe people may think of is just a standard square structure. Very common, the type of structure that atoms would want to form into. But there's other different structures, and that's what they're showing here, is that water actually prefers to go into this type of structure, and this causes it to actually be bigger. That in its solid state, its volume actually grows because of water's preferred structure to be in this larger state than, say, in just a simple cube structure. And so that's just a unique property of water that they're talking about, on how it is unusual that water has, that when it goes from solid to liquid, that it actually becomes a smaller volume. Because normally, what happens with most materials, when I mean normally with most materials, is that when the atoms are bouncing around in their liquid state, going all their different directions, that usually when they form a solid, that becomes a little bit smaller in space, is usually what happens when you, and that goes back to, in a sense, thermal expansion. When you cool things down, they tend to get smaller in size, and you warm things up, they tend to get larger. A similar effect here. When you cool a liquid and it goes into the solid state, its volume tends to become smaller. But as you heat it up and it goes into the liquid state, its volume tends to get larger. And that's what most materials do, and that's where water is, again, something unique. It doesn't follow that traditional pattern from its solid to liquid stage. And so just an interesting thing there. That's all meant to be an interesting topic. I think this is kind of interesting, too. They're just giving you a short explanation on why ice is slippery, because at the very top of the surface here, the crystalline structure breaks down, and it becomes a little surface of water that's right above the ice, right above the crystal structure there. And that's what gives water a slipperiness to it. So, and just to say again, there's no equations here for Chapter 15. All just concept ideas. I think for the most part, people have pretty straightforward understanding of heat, that heat flows towards things that are cold. I guess maybe the big thing is that maybe some people think that getting cold is you're gaining something, where I would just, I guess, remind people that getting cold means you're losing your heat. That's what cold is. You're losing energy. And let's check out the homework questions. All right, so checking out number 1. Which of these values is the lowest temperature? So this is just to get you some acquaintance with the different energy scales. So 0 Celsius is the freezing point of water. That literally equals mathematically, that is the equal sign there, equals 32 degrees Fahrenheit. Those do equal. And just to say really quickly, if you're thinking to yourself, well, 0 doesn't equal 32, that's absolutely true, but the units make all the difference. So, for instance, you all know 12 inches equals 1 foot. You all know that, but we also know that 12 doesn't equal 1. So the unit makes a huge difference on why we can equate these two. And I don't think this was stated anywhere, but the freezing point of water is also 273 Kelvin. So Kelvin is the official science scale because in science we found that there is a lowest temperature. And that's how the Kelvin scale is assigned, where physics has found the lowest temperature to be, well, we call that 0 Kelvin. And so Kelvin, a little bit more objective basis on how we define that, where Celsius and Fahrenheit are completely subjective on how those were chosen. So anyways, A, B, and D are the same values. Those all represent the freezing point of water. So what's actually lower here is 270 Kelvin. That's 3 degrees below the freezing point of water. And so this was a part in the book I was reading I didn't mention. There's a part where they say scientists like to prefer the word internal energy, and that's true in some respects, but I wouldn't want to give the impression that heat isn't used either. So when you have some object, it really depends on the context of what you're talking about. It is true that in physics we do talk about the internal energy an object has, which has to do with all the particles and what their bonds are inside whatever structures they form. But when we talk about how this energy moves around, then you tend to say heat, that the heat is moving this way. I don't think I've ever heard anybody say the internal energy flow. Usually people will say heat flow. So I would say both words are used. It just really depends on the context. So they are talking about heat. In which direction does heat naturally flow? And it flows from hot to cold, or from high temperature to low temperature. And that would be this one, from high temperature to low temperature. And why that is just a fact of nature. There are things about nature that we just accept in physics as being true. So for instance, we notice in the universe that everything seeks its lowest energy state. Things just want to be in the lowest energy state possible. And that's just the way the universe works. Why that actually is, I don't know if anybody has a definitive answer on that. But there are things we just accept as being true that we can't necessarily prove. Just to give you another example really quick, like this pen, the pen isn't just going to magically disappear, that it has some permanence to it. This pen won't just disappear, and this is actually called object permanence. Why does this pen just remain here and not just disappear or just come back? There's some permanence to this object that it just won't go away. And why is that? Is just something we accept about the universe, that my pen's not going to just disappear. It's going to be permanently there. There's some permanence to this object. So there are things that, we can't prove, and there's certainly many things we don't know. This is the question I was talking about earlier when looking through the book, and I couldn't find the specific section looking back, but if you're reading through it, there's one paragraph that talks about iron, silver, and water. And it's just talking about if you're boiling things, and you'll find this answer only in this one paragraph, which I think is a little bit unfortunate. So just saying I'm not going to do this to you on the test here. That's a little bit too specific. But water has a very large heat capacity. Iron has not as large, and silver's is an even smaller. And they say that in this one paragraph where they compare these two. So if you're thinking where you're supposed to know that, it is in this one paragraph. Overall, water going to have the highest of all these here. Soil, I don't even think they mentioned soil. I didn't see that anywhere. But check it out. Some other ones. Oh, here it is. This is what I was thinking of. Which warms up fastest when heat is applied? Water, iron, or silver? So if you're checking out the practice problems and you come across this and you're thinking, wow, how am I supposed to know that? This was the question. that was in a very specific part of the text. And I'm just going to give another quick attempt just to see if I can find. You know what? I'm going to pause a second and find it. All right. So it's back here with the dude eating a piece of pie. It's this paragraph right underneath the pie eater. And they're saying different substances have different specific capacities for storing internal energy. Again, internal energy is heat. So if we heat a pot of water on a stove, it takes a lot of energy to increase it by 1 degree. It takes a lot of energy to increase water by 1 degree. And then they say, but if we put, so I'm looking at this kind of mid-sentence here, but if we put an equal mass of iron, well, the iron, so they're saying the water is going to take 15 minutes to change temperature, but the iron's only going to take 2. So iron must have a smaller heat capacity. And then they say silver will warm up in less than a minute. So silver takes a very little amount of energy to change its heat, change its temperature. And this is the only place they say that is in this one paragraph right here under the pizza or the pie eater. And well, that's how you're supposed to know the answer for this one. And that's a tough call. To be able to find that. So just wanted to point that out to you. But our final answer here, silver warms up the fastest, then iron. And, oh, no, I'm sorry. That says, warms up faster than water. So that's the one we're looking for, that last one there. Which generally expands more for an equal and competing temperature, solids or liquids? So did we talk about that in the book? Let me check that out. All right, so just a quick splice. I noticed in editing I lost a clip there. But coming back to this liquids and solids one, and I was looking in the book where to find that. And that was when they were talking about thermal expansion right here. And in the clip that was lost there, I was talking about it would have been nice if they had a thermometer, one of those kind of old school thermometers, where you got the tube of mercury in it, and the mercury rises to some point, and then that's how you measure your temperature. Oops, I got this in the way here. And that's how you end up measuring your temperature, where the mercury rises. As heat comes in, it warms everything. It warms the whole thermometer, all the heat coming in does, but you only see the liquid rise. And now while everything is expanding, it takes a lot more energy to expand solids. And so you don't see, it's not like you see the thermometer get larger as it heats up. What you see is the liquid get larger as it heats up. And so this is a thermometer is a nice visual evidence of seeing liquid expand while the solid doesn't. And the thermometer is a good example of that. And it just would have been nice if they had a picture of a thermometer here in the expansion picture here. And that's how I ended up checking this. And there's, I'm just going to skip to it, I guess. The next problem also got snipped a little bit here, so I'm just going to do this one again for this 1 meter bar. And what I think is a little bit unfortunate here is they say 0.4 centimeters, which is unfortunate because, I don't know why that's blurry, because there's a change of unit here. So 0.04 centimeters is actually 0.004 meters. And if you want to look at what percentage this is, well, percentage times whatever your number is going to equal what your output. So just a simple percentage equation, and then you can find what the percentage is. It's 0.004. Now remember, if you put things in percentage, you have to move the decimal place twice. So that's actually 0.4%. And when they go to the 100 meter, so now that I have a 100 meter long bar, well, our initial data shows us that it only changed by 0.4%. And so we're going to take 0.4% of 100. And if we take 0.4% of 100, we'll get 100.4 then. And so the 100 meter bar will stretch then by 40 centimeters. And that's how I ended up getting my answer here that I typed in, 100.4. And I don't know what's happening. I lost some clips. I can see this is blurry. But Only a few minutes there. It was bad. So there is the homework. I will talk to you next one.